So I'm going to talk about the LearnI project, which is about learning data integration. And so my goal here is not to go into detail of the project, and I realize I haven't listed our collaborators and our team because my goal was more to pitch the problem and the fundamental tools that we want to use, because this project is really uniting several threads that are present in other projects, and I think it's really important that we build up collaborations. And in particular, I don't know if I mean, basically this project is trying to unite statistics and database problems. I'll start with giving the application context, general application context. Then I'll discuss the overall outline of the project, and then I'll give a few preliminary work that we have already done that is a start in this direction. So in terms of application context, there are really two application contexts that are of interest to me. One is studies in social sciences and in health. And another problem which is related is the problem of dirty data that I'll describe. In terms of social sciences and health, and actually many sciences, one of the important challenges is to assemble different health or social sciences databases. And the reason we're doing this assembling is because we want to ask questions to this data. We want to ask questions such as, what's the prevalence of pathology as a function of age? We want to do prediction models, such as a prognosis, so can we predict an individual's evolution? We might want to come up with causal claims, such as identifying risk factors or causal links in the data. And when we're doing this, it may be important to work across multiple sites and across multiple databases. And one of the reason why it may be important is that accumulating multiple sites and multiple databases bring more general conclusions. It also brings more statistical power. So we've been doing this, for instance, in brain imaging, and something that stands up is that ingesting each data set requires a ton of work, because it requires what database people call alignment, which is to find correspondence in the information. And this is hard, and this is typically done by hand, even though there is, of course, work to do this automatically, but it's a very challenging problem, and it can't always be solved automatically. And another related challenge, even in a single database, is that the data must be denormalized for analysis. And what I call denormalizing is going from a set of multiple tables, information that is spread across multiple tables, to a single table that I can feed in a standard statistical model. And this can be very challenging because it requires basically understanding the way the data is represented in the database and crafting those denormalizing queries. And so these problems are related to the problem that is known of data integration, which is a fairly typical database research topic. And I'm not a database researcher, so of course I have imposter syndrome here. And now there's another problem, which is somewhat related, is the problem of data science and dirty data. And so if I'm a data scientist, I want to use tools such as tools of statistics to get meaningful answers. This is why I do this analysis. I may want to have a claim on society, a claim on the brain, but there's a well-known fact is that most of the work is actually to prepare the data. And there's this famous quote that 20% of the time is spent preparing the data, and 80% of the time is spent preparing the data, and 20% of the time is spent complaining about the need to prepare the data. So this is something that we've found a lot talking to people who use our statistical tool, is that the hard problem is to feed the data in the statistical tool. Once you've done this, you've solved most of the problem. So if it's a hard problem for someone, it's an interesting research question. And so now the question is why do we have this problem? Why are people struggling? And one thing that strikes me is that most, by huge majority of the statistical learning research starts by assuming the data lives in a vector space or in a metric space, but in some continuous space that has some regularities. And if you go to NeurIPS, for instance, that's 95, maybe more, of the papers. And in the best case, real-life data science, you get tables like this. And what's the problem? Well, first, I have missing values. Missing values don't live in a vector space, and I'll claim that this is the reason why they're challenging. But then another problem that you have is this column, which contains non-normalized information. This information is structured, there are latent categories in it, but it's not normalized. So what do? We curate it. We normalize it in a certain way, either with a normalizing algorithm or by hand. And then, this is the best case, but what you might have is you might have missing column names. This is often the case. So then, or the column names across the different sites don't match, and so then you need to align them. And finally, the real problem is that often you have multiple of these tables, and you need to do the analysis across the tables. And none of this lives in a vector space, and I must admit my comfort zone is the vector space. Outside of a vector space, I'm outside of my comfort zone. So that's the point of view I gave you right before was the point of view of statistical learning. Now, if we take the point of view of databases, which is an interesting and complementary point of view, so databases have tackled the problem of data assembly for a long time. And the way that this literature works is that data of different nature will be assembled by using common entities across data of different nature. So for instance, I want to assemble patient characteristic and population because I want to do an epidemiological study of health with regard to pollution. And I will use the fact that I have two tables and that there is a common entity between the two, which is the city. And so I can do a join across this, and I can denormalize my data, and I can build a table with which I can work. And so for this, there is a huge amount of work that is basically built around the relational algebra and database techniques to do this aggregation and this denormalization. And now this breaks down if I have error in the symbols, because then the common entities don't bridge the gap. So once again, errors in the symbol break everything. And so I'll claim that there is a really fundamental challenge here, which is that we have a mix of numerical data and symbols, and we have errors. And there's no topology or no metric on the symbols. And this is very hard because it's very hard for me to do a model of my noise. It's very hard for me to impose some statistical regularities on the model. So I will claim that the fundamental challenge is that of symbols or entities with noise that are linked with other source of information. And this is what we're interested in LearnI, and we're interested in doing statistical analysis with this kind of challenges. So then I'll present a bit the project, which is to develop analysis techniques on databases that rely on embeddings. And so the overall strategy is that we're not trying to do data cleaning. Our goal is not to produce a clean matched database. We will not create and assemble data. Rather, we will build a statistical model that will answer a given analytic question from the dirty data, directly from the dirty data. And our philosophy is that we're going to build on embeddings and continuous models. So we're going to try to represent all the information, including the discrete information in vector spaces, because that's my comfort zone. And beyond it being my comfort zone, there's an intrinsic reason for shooting for those continuous valued representation, is that they can capture some form of regularity that will allow interpolation, extrapolation, and regularization. And we will also strive for models, in particular statistical models, that can be fit with gradient descent. So some form of stochastic gradient descent. And so basically, this is the toolkit of deep learning or differentiable programming. Yeah. So the overall axis are the following. In the first part, we will focus on building representations. So the idea being to embed all the data in a vector space. And there is an existing literature, a quite large existing literature, from which we will borrow, typically in fields such as natural language processing. Knowledge-based embeddings have also been developed. And we will definitely borrow from this field. What we will adapt is that natural language processing uses a specific regularity of the language, which is that it's a sequence. We have a different structure in a given relational database. And the existing embeddings of entities in knowledge bases do not use the numerical values. And in most of the health or social science databases that I work with, a significant fraction of the data is made of numerical values. So if I'm going to throw away this information, I'm throwing away a huge amount of information. Once we have representations, so we'll work both on representing and on aligning. Once we have representations, we'll work on transforming those representations to assemble. So if I have different representation of different sources over a different type of data, how do I assemble this? And for this, I need to replace my relational algebra with vector operations. And finally, we will put this in a supervised learning framework or in a semi-supervised learning framework, and we will optimize those representations and those operations. So I'm going to go quickly because I'm running out of time, but for embedding entities, the crucial idea is that we're going to rely on the context. If we need to solve alignment problems, we will use basically distribution matching approaches. In terms of transforming, we need to adapt things such as selection and aggregation. So that's basically some advanced form of pattern matching. So it's supervised learning. Joins are harder because when we need to adapt the joins, we need to match two tables and transfer attributes. So it's about recasting this in a continuous framework, and all this being differentiable, of course. In terms of training, this is more classic. We're going to be relying on stochastic gradient descents and stochastic regularizations. One of the challenges is that in a complex database, I have very different type of entities. I might have patients, but I might also have doctors. And I might not want to do a supervised learning algorithm that forgets the difference. So I will need to identify specific irregularities in my database and use them. And we'll also try to develop transfer learning to be able to reuse representations and part of an architecture. Because this is one way of decreasing the sample complexity of those models. And we will also focus on a few application tasks where the focus will be to enable easy reuse of public data and of health data. And we will work on learning representations of public data, such as the data you can find on data.gov or data.gov.fr. Because there's a huge amount of numerical data sets that are there and that are hard to reuse and integrate. And we will apply this to health problems, in particular opportunistic epidemiology, including things such as the electronic health records of APHP, the Paris hospitals, and we started working with them actually for the COVID 6 months ago, and those problems of dirty data and assembly really do apply there. Okay, I'm going to say a few words on some preliminary work that we've done, and basically what we've developed is that we've developed models that can embed string entries using the irregularities of those string entries. So basically we're using that some strings are similar to embed them. And really if we look at this column, the idea is that there's a lot of repetition of substrings. And so if we can, identify latent substrings and use this to build an embedding, this can help statistical analysis. And the technique is basically that we do counting of substrings, whether it's character level or word level substrings. And then we can build a statistical model on this, and it's some form of latent factor model, so it's going to end up being some form of matrix factorization, one way or another. And so it's some form of, basically, of topic modeling. And so once you do this, you can have a method that takes, this uncurated set of strings and basically find a representation. This is a real experiment. Finds a representation that finds latent categories. And you can even have tricks to name those latent categories. And then what we've shown is that by doing this, you can have good statistical analysis without manual deduplication. Because the typical process is to deduplicate to find the variants of the strings that relate to the same entity, deduplicate, and then do analysis. And what we're showing here is that with those continuous representation, you don't need deduplication and it works better. And more recently, we've run an experiment where we use these kind of techniques across multiple databases, and we compare to state-of-the-art manual matching, because manual matching, well, it's semi-manual matching, but basically matching supervised by an operator is what works best to match concepts across databases. And what we show is that embedding brings you more benefit than manual matching, and what works best is embedding and manual matching, but actually the benefit is quite small. Okay, so that's all I have. And once again, this research is in between statistical learning and databases, and I think basically I welcome really discussions and thoughts and collaborations from both fields. Thank you.
Questions? Okay, a very short one. So first you have these embeddings, and then you have your statistical processing. Does the performance of the processing helps you to redesign the embeddings? I mean, you have this kind of forward, backward.
Yeah. So an idea that's behind your question is that we probably would want to backpropagate to improve the embeddings. So we haven't started on this. That's part of the idea. This is why we want to make the assembly differentiable. I suspect that in many settings we won't have enough data, so something that will be crucial will be to do self-supervise, where we're going to create pretext tasks in the database to improve the embeddings based on pretext tasks. So in a sense, if you want an analogy, we're looking at things that are a bit similar to transformers, where you create a pretext task. You build an architecture with internal continuous representations that is optimized for this pretext task, and then you can transfer this, for instance, by fine-tuning it.
Maybe there are some cases of polysemy, like an officer or stuff like that. Have many meanings in many different contexts. So I'm wondering at the end how you deal with that. So will you be able to relate to some definition of the terms that will encode this polysemy? Would there be some knowledge base behind? How do you stabilize this kind of uncertainty of the meaning?
So there are different parts to your question. One is how do we deal with polysemy, and part of this is a classical problem in identity recognition, for instance, in natural language processing. And what recent history has shown is that the way you deal with polysemy is by context. So basically, you need to embed not only the entity but also the context. And there was Elmo vectors before BERT. Elmo vectors would do this. They would do embeddings, and then they would do embeddings of the context. And then the question is also, can I relate to a knowledge base? And so in the proposal here, we've basically said, well, a knowledge base is another form of relational graph. So of course we can. In practice, to do this best, we would have to adapt a bit the strategy. And this is one of my dreams. If you give me a table, can I do named entity recognition in this table? And can this help data ingestion?
Okay, thank you.